Hello students, welcome back. Before resuming our discussions in section 2, let's have a brief recap in section 1. We went through the idea of vector functions and we saw that vector functions define curves which we call parametric curves. Here are some examples. A parametric curve, in this case a line, defined by a vector function. X is like this and y is like that. Put together we have a vector function. Another example, in this case an ellipse. X is this function, y is that function. Put together we have a vector function. And that gives me this curve. Third example, x and y are like those. Put together we get a vector function which creates this parametric curve. By the way, here, time variable t is often called a parameter. That's why these things are called parametric curves. And then here's a third example. T is our main variable, but it is often called a parameter, and that's why we call these curves parametric curves. Now, for parametric curves, let's consider tangency problems. And it goes like this. Remember? What we want is this, the slope point equation of the line. Y equals m, the slope, x minus x0 plus y0. x0 and y0 are easy to find. Just plug in t0 into the function x and function y. That's going to give me x0 and y0. No problem there. The slope is a problem. What is slope? You gotta remember this slope formula. The slope is rise over run. The difference of y-coordinate over the difference of x-coordinate. But we want tangent line, so infinitesimal over infinitesimal. We have dy over dx. That's a derivative, but then again, this is parametric. We want variable t. So take the derivative with respect to t, we get dy dt up there. And take the derivative by t, we get dx dt down there. And look at this. The bold part. That part works exactly like the ordinary fraction, which cancel out this dt and dt. That's the nature of the chain rule. So in the end, what do you get? dy over dt, which is the derivative of y prime, over dx over dt, x prime. So we have y prime over x prime. This one here, y prime over x prime. That's the slope formula. Remember that. Okay, let's go to the next problem here. X is cosine of 2t, y is sine of t. I could have given the problem like this, or I could have given you a problem like this. X of t, comma y of t. And then put together like this. It's the same. Here I gave you x and y separately as two functions. Here I put those two together and gave you a vector function. They're the same. X of t is this, y of t is the second, and then t0 value. Let's see, we have this kind of curve. Okay, alright. Let's find the slope of the tangent line. Oh, excuse me. Slope is the most important part, but point first. Point is easier, so let's find the point first. x0 is x of pi over 6. So that's cosine of 2 pi over 6. So cosine of pi over 3. And that's 1/2. Did I do this right? y0 is y of pi over 6. And the sine of pi over 6. Oops. And what is sine of pi over 6? Sine of 30 degrees. That's 1/2. So that's 1/2, and that's 1/2. We can anticipate our solution like this. Y equals m, x minus x0 plus y naught. X naught is 1/2 here, y naught is 1/2 there, and the slope, that's always a problem. Slope is always a problem. Okay, alright. X naught done, y naught done. Let's go to the slope. Slope formula is y prime over x prime, so let's find the derivatives. X prime will have cosine functions, so negative sign. Inside never changes, and by chain rule, we have to multiply the derivative of the inside. So x prime evaluated pi over 6 is negative 2 sine of 2 pi over 6. Nobody writes like this. 2 pi over 6. What is this? It's pi over 3. So it's negative 2 times square root of 3 over 2. So that's negative square root of 3. Did I do this computation right? Okay, how about y prime? Y is sine of t, so derivative is cosine of t. And y prime of pi over 6, that's cosine of pi over 6, and that's square root of 3 over 2. Cosine of 30 degrees. Okay, y prime there, x prime there, so we can find out the slope. N is y prime over x prime, evaluated at pi over 6, of course. So this is square root of 3 over 2. Over x prime, negative square root of 3. So this entire thing is what? Negative 1/2? Did I do this right? Please check. Y prime over x prime, square root of 3 over 2 over negative square root of 3 simplifies it to negative 1/2, and that's gonna go here. Therefore, y equals to negative 1/2 x minus x naught, which is 1/2, plus 1/2. There goes the slope of the tangent line, point, and then the equation of the tangent line and the slope point equation of the line. Step 1, x0, y0. Step 2, derivatives. Step 3, slope. And step 4, the equation. Same thing, we have been doing it for a number of weeks, for graphs, for implicit curves, now for parametric curves. What we have here, that's a solution. First a point, yes, plug in, calculate. The derivative, okay, just a derivative computation, first component, second component. The slope, y prime over x prime evaluated at t naught, negative 1/2, and then the equation, the slope point equation. Exactly the same as before. And then we have visualization, alright, that looks like a tangent line. We have 2 more problems. Stop the playback and try on your own. Let's see how much you can do. If I remember correctly, this one has some tedious computation. Let's do D first. It's going to be a bit better. Again, stop the playback and try first, but assuming that it's done. Okay, alright. Step 1, x naught, y naught. Just plug in pi over 6 and do your computation. Ready? Here we go. Plug in pi over 6 and do your computation. We have sine of pi over 3, so that's square root of 3 over 2. And then cosine of 5 pi over 6. And then that's negative square root of 3 over 2. So after simplification, we get pi over 3 comma pi over 6. Derivatives. Well, we have a bunch of constants here, so they go out. We have 2 and 1 there. We have sine, cosine, so this one becomes cosine, this one becomes negative sine with some chain rules, so be careful about those coefficients. Okay, and then the slope. It's y prime over x prime evaluated at pi over 6, so you must do your computation. Can you see it? This one here, plug in pi over 6. This one here, plug in pi over 6. And do your simplification. Negative 2/3. We have the point, we have the slope, we have the equation now. Here's the visualization. At pi over 3 comma pi over 6, right here, we have a tangent line. Does it really look like a tangent line? It's a little bit difficult to see. Yeah, it looks like a tangent line. If I stretch this picture sufficiently, then I can see it. Yeah, it's a tangent line. So, can you apply the 4-step process again to this one here? Stop the playback and try. Okay, go ahead. Step 1, the point, plug in. So plug in t equals 1/4, e to the 1/4 power, cosine of pi over 4. Cosine of pi over 4, 1 over square root of 2. Sine of pi over 4, again 1 over square root of 2. So we get this expression. Can everybody read it? E to the 1/4 power over square root of 2. Now the derivative. Well, we have to use the product rule, exponential times cosine, exponential times sine. But when you take the derivative of cosine, you have to use the chain rule. The derivative of the inside pi comes out. So we end up with this kind of computation. Product rule first, and then here, this pi came from the chain rule. This pi came from the chain rule. In the end, we get this. And then the slope, y prime over x prime evaluated at t equals to 1/4. Can you read it? Maybe not even that. So plug in, and then do your computation here. Y prime over x prime evaluated there. So e to the 1/4 power will all cancel out. And then sine of pi over 4, cosine of pi over 4, they're all the same, 1 over square root of 2. So they all cancel out. We get 1 plus pi over 1 minus pi. Consequently, we get an equation like this. Y equal to m x minus x naught plus y naught. X naught, y naught we found out in step 1. And then the slope we found out from step 3. Okay, so much for tangency problems for parametric curves.